Okay, so continuing on this problem on water that is flowing on a 1-inch schedule for the steel pipe, given the velocity, the entering bulk temperature, and that of the temperature of the heating medium, which is steam. And you're also given the heat transfer coefficient, and that is the convective heat transfer coefficient based on the outside fluid. And now we are to continue on letter C. You are required to determine the heat transfer rate, that's Q, for 0.305 meter pipe with the water at an average temperature of 65.6 degrees Celsius. So I'd like you to get a screenshot of this problem. So if you already have it in your notebooks, so there's no need for you to take a screenshot. I'll just take a screenshot of it, and then I'll share to you the Jamboard where we can continue with the solution to this problem. And that would be for letter C. So I'm going to share again different screen. Because, can you now see the Jamboard? The blank board?
Yes, Miss.
Thank you. So we go now to letter C. So for letter C, you are required for Q, the rate of heat transfer, and we can use the values that we got from letters A and B. So we can use the formula UI, then the area based on the inside part of the pipe, and then you have the outlet and the inlet bulk temperatures, the difference of the outlet and inlet bulk temperatures. Now, this particular expression is also equivalent to the difference in temperature divided by the summation of all resistances. So convective heat transfer based on the inside part of the pipe. Then we have the conductive heat transfer of the pipe material itself, and the convective heat transfer resistance based on the heating fluid, which is the steam. And that would be our summation of R. So in either of these two formulas, you can solve for your Q. So whichever is more comfortable for you. Now, in our letter B, you determine the overall heat transfer coefficient, and we're going to use that in this case. So we're not going to solve it in this way because you're accustomed to solving it in that manner. But you can also do so in checking your answers whether the two would really be correct or more or less be similar or nearly equivalent. So what's the answer that we got with U sub I for letter B? If you may, you can place it on the chat box. I can read it there. Based on your notes, what's the U sub I that we got from letter B? Because in letter B, you were asked to determine the overall coefficient of heat transfer based on the inside physical characteristics of the pipe. So do you have the answer for that? It's the answer for letter B. Do you have it? If you have, can you please place it on the chat box? Are you there, class?
Wala pa yung tatlo, miss. Wait.
So I'll use the values that were given on the reference material itself. So for the U sub I, the value is 4586. So it's the overall heat transfer coefficient with the same set of units as the convective heat transfer coefficient. And its value is 4586 watt per square meter per Kelvin. Then you're going to multiply it with the area based on the inside diameter of the pipe. So in that case, your area will be the lateral surface area, and that would be pi. And then the inside diameter, which was given to you, which is 0.0266. This is in meters. And the length of course, which is 0.305 meters. Now, in this case, you will already have the Q after you, of course, multiply by the temperature. So if you're going to multiply with the temperature difference, so the temperature of the heating fluid, which is the steam, is 107.8. And that of the water is 65.6. So these temperatures are in Celsius. So that would be okay because we're dealing with difference. So a difference in Kelvin and Celsius would just be the same. So in this case, now you have an answer in watt. So the rate of heat transfer will be 4,935 watts. So that's the requirement for letter C. If you use this route, difference in temperature, so the difference in temperature is still very much this one, 107.8 minus 65.6. So that's degrees Celsius. Now, your summation of resistances, as I have mentioned, will constitute the resistances on the inside and outside film of fluid of the pipe and the conductive heat resistance of the pipe itself. Now, the value of this summation of R is 0.08. We've got this last meeting, or 0.008 008 552. So that's your summation of resistances. So in this case, this is what per degree Kelvin. Oh wait, that's not the set of units for your resistance. So if our unit should be in watt, so this particular summation of resistances should have a unit of degree Kelvin or degree Celsius per watt. So we can cancel this, and what goes up is the watt. So your answer would still be the same and should be the same at 4,935 watts. So either which of the two equations you used, the one which is fundamental, I'd like to call this the fundamental formula, which is the driving force divided by the resistances, the summation of resistances, or this formula based on the overall heat transfer coefficient, you're expected to have the same value. So you can check from your end if you're still going to have the same answer for the second formula that I have shared. So 4934.51, which is 4935. So basically more or less the same. So any question with this? This is a continuation of the problem that was just read a while ago concerning water flowing inside the pipe being heated by steam flowing outside of the pipe. Any question here? Okay, so if there's none, I'd like to go back to the document for part 1 of convective heat transfer. So that ends the solution for this letter C. So we have here, I've shown this to you on how you're going to get the characteristic of your pipe based on the schedule number and the nominal size of the pipe. And I've shown this appendix also based on the properties of water. So you need the temperature, that way you can get the very important properties like the mu, the K, the Prandtl number. And then, of course, the density and the CP, should there be a need for those properties. In this appendix here, you have the thermal conductivities of common substances, specifically metals. And in here, if you remember last meeting, I will annotate. If the steel that is mentioned is not specifically identified, whether it's a 308 steel or a 304 steel or a 1% steel, so we use this one, the 45. The steel having 1% carbon at a maximum temperature of 100 degrees Celsius. So this is the K that we used in our problem, in the previous problem specifically. Okay, so this is taken from the appendix of Gian, who please. You may as well refer to section 2 of Perry's for a more comprehensive list of materials, not only metals, and their corresponding density, CPs, and thermal conductivities. So I will clear my markings here if there aren't any questions. Okay, so I'll clear my marking now. Then we'll proceed with liquid metals and their corresponding heat transfer coefficient. So if we have a problem concerning a liquid metal, the Nusselt number formula that you're going to use are these two, depending on the Peclet number that you were able to predetermine. So meaning you're going to determine first the Peclet number. So we know what the Peclet number, it's the product of the Prandtl number, I think, and the Reynolds number. So let me see. So as a review, okay, so this is your Peclet number, the product of the Reynolds number and the Prandtl number, as I have mentioned. So I'm just showing to you that part of the slide where you're going to look that up. So you need a predetermined value of the Peclet number, so you can choose what would be the right side of the Nusselt number formula. HLD over K you will use. So if it's on the range of 100 to 10,000, this will be the right side of HLD over K. If it's greater than 100,000, so it could be this one. For these two formula is good for a ratio of L to D greater than 60. Okay, so for a portion in here, like 101, until this one is only until 10,000, but this one does not have any limitation as long as Peclet number is greater than 100. So you can choose this one if Peclet number is greater than 100. Okay, now here is a sample problem on liquid metal heat transfer inside a tube, so which we will be using for this particular formula, set of formula. Now a liquid metal flows at a rate of 4 kilograms per second through a tube having an inside diameter of 0.05 meters. The liquid enters at 500 Kelvin and is heated at 505 in the tube. The tube wall is maintained at a temperature of 30 Kelvin above the bulk fluid temperature. So take note of the phrase that the tube wall is maintained at a temperature of 30 Kelvin above the fluid bulk temperature. And there's a constant heat flux that is to be maintained in the process of heating. Calculate the required tube length for this problem. So you're given the physical properties of the liquid metal. We do not know the identity of the liquid metal. So its physical properties are given here. You have for viscosity, you have for density, for specific heat, and for its thermal conductivity. Okay, the K, 13 watt per meter per Kelvin. So if you can take a screenshot of the problem now, we'll proceed to the Jamboard and have the solution run through, how we're going to find the value of this particular uh, tube, specifically the length of the tube. Okay, please take a picture of the problem so you will have a basis on what we're doing or determining as we go along. Okay, I'll now share Jamboard. We'll go back to Jamboard and we'll proceed with this new problem. So you're given a liquid metal that flows at a rate of 400 kilograms per second through a tube having an inside diameter of 0.05 meters. Oftentimes, the liquid that is to be heated flows inside the tube. So we'll have here the liquid metal. I'll just have it as LM. So it's kilogram per second. So it's mass flow rate. So the ID of the tube is given. So the bulk fluid entering temperature is 500 Kelvin and is heated to 505. So meaning the outlet temperature here is 505 Kelvin. The tube wall is maintained at a temperature of 30 K above the fluid bulk temperature. So this tube wall. So 30 K above the bulk temperature. So we'll have this as 30 K. I'll place it here, boarded for now, above bulk temperature of the fluid. And the problem says that this is a constant heat flux problem. So we'll place here, Q over A is constant. And then you have the summary of properties for the liquid metal. So you have its viscosity. You have its density. The CP. And you have the thermal conductivity. Okay. And in this problem, you are required, just place the required information here. You are required for the length of the tubes, and that's L. Okay. Now, based on the picture that you have taken a while ago, is there anything you'd like to add here, or this is okay already? If you have any questions. Okay, so I think there's none. Okay, if there's a question, just write it on the chat box or you may use your microphone there. So we'll proceed with the solution. Now we need to establish the Pecklet number, so we will know the correct formula to use for the Nusselt number in this case. So your Pecklet number is the Reynolds number and the Pronto number multiplied. So if this is our equation 1, we'll have it labeled there. Now we'll determine Reynolds number. So Reynolds number is the mass velocity D times the G, the mass velocity G times the diameter of the pipe divided by the viscosity. So this is the mass velocity, this is the diameter of the pipe, and this one is the viscosity. Now in this case, we need to determine our area, the cross-sectional area of the pipe. So we'll have this first as 2. So if we'll find the cross-sectional area of the pipe, that would be pi d squared divided by 4. And if we'll use the value that we have here, the inside diameter, so you will have pi times 0.05 squared divided by 4. Now, this should give you an area of 1.963 times 10 raised to negative 3 square meter. Now, the purpose of this area is for you to be able to convert this pure mass velocity to mass velocity in terms of fluid flow, which is per unit area. So you need to convert this m dot to G. Okay, so any questions so far with the A value here? So with the G, you're going to use the m dot, the pure mass velocity, and the area that we solve here. So we'll have your m dot is 4 kilograms per second. And we divide it by the area that we just solved. So 1.963 times 10 raised to negative 3 square meter. So this is your velocity per unit or mass velocity per unit area. Now, in this case, your answer for the G is 2.038 times 10 raised to 3. So, of course, kilogram per square meter per second. And this is the G that should be substituted here on your Reynolds number. So you can now get your Reynolds number. So from equation 2, from the previous page, your Reynolds number will be the inside diameter of the pipe, 0.05. We multiply it with the G, this one, 2.038 times 10 raised to 3. So dg over viscosity. So the viscosity is provided by the problem, 7.1 times 10 raised to negative 4. Now you will be getting a Reynolds number value of 1.435 times 10 raised to 5. So you're done with Reynolds number. Now you can go to the Prandtl number. Again, which we need to solve because we're not given the identity of the material. So your Prandtl number is Cp mu over K. So given is the Cp here. You'll have the Cp of 120. Okay, viscosity of 7.1 times 10 raised to negative 4, and a thermal conductivity of 13. So you'll get a Prandtl number of 0.00655. And you can substitute these two values of the Reynolds number and Prandtl number to equation 1. So you'll have Pecklet number. So from 1, you have the Pecklet number now. So 1.435 times 10 raised to 5. We multiply it with 0.00655. So you have a Pecklet number. What's your Pecklet number in this case?
939.
Times 1.435 exponent 5. Okay, and 939.
0.925.
Okay, we'll just round this off to 40 so we won't have to deal with decimal. So we'll make it 940. So you have it as 940. So based on the choices that you have, actually you can use the first one or you can use the second one because the second one says the second formula is good for Reynolds number greater than 100. And the other one is also for Reynolds number between 100 and 10,000. So either of the two will do. But since the first one is easier, it's not as cumbersome as the second one. So we'll use the first one. So I'm referring to this. I'll go back to our the document that I was sharing to you. Okay. The Pecklet number that we solve can be any of these two here. But the first formula is easier because it doesn't have this particular 5.0 plus 0.025 and PE raised to 0.8. So we can use the first one, the 0.625, because anyway, it's still complying with the condition that it should be greater than 100 but less than 10,000. Okay. Now, in terms of L to D ratio greater than 60, we don't have a way of checking it for now because actually we're determining the L. Okay, so we'll just check if it's still conforming with this particular formula. Actually, the two formulas is for L over D greater than 60. So we're going to use the 0.625 and PE raised to 0.4, but you can also use the second one if you want to. Okay, so I'll go to the jumper again. Excuse me. So for your HL, for your Nusselt number, which is HLD over K, we'll use the simplest formula of the two, the simpler formula of the two, 0.625 and PE raised to 0.4. From here, you get to solve for the HL. So we'll just transfer the K and the D on the other side, and you'll have here 0.625 and the Pecklet number 4. Now, for the thermal conductivity, we have 13. And for the ID, we have 0.5. So you'll have 13 here, and you have 0.05 here, and you have 0.625. And the Pecklet number that we got, which is 940. The 940, which you need to raise to 0.4. So you'll be getting an HL value. Is it 2512 watt per square meter per Kelvin?
Yes, miss.
Okay, so it's 2512. Now, after you have the 2512 for the HL, you can solve for the Q based on the another fundamental formula for heat transfer, whether we're considering purely conductive, or a combination of the two, or even considering all three forms or modes of heat transfer. Now, you have this known as early in your physics, that Q is equal to mCp delta T. Now, this would be the same Q that could be solved using your Q. Okay, I'll just have this one. You have this formula Q. So this is our third equation already. And actually, the Q that you have here is the same Q that you will be getting here in the heat flux, which is HL delta T, if we're going to consider convective heat transfer. So this is the fourth. So we're first going to determine the Q here, and we're going to place it in there. Okay. Now, your Q from 3 is equal to, so you're going to use the mass velocity, the pure mass velocity that is given in the problem. What was that? That's 4 kilograms. 4 kilograms per second. I'm using this equation first. So 4.0 kilograms per second. And the CP, 120. 120 joule per kilogram Kelvin. And then you have the temperature. So that would be the outlet and the inlet temperature. So 505 and 500. So you have 505 and 500. So this is in Kelvin. So you get to cancel the Kelvin unit, you get to cancel the kilogram units, leaving you with the joule per second. So in here, you will get a Q value of 2,400 watts. Check. So 120 times 4 and times 5. So 2,400 watts. So that would be the Q that you're going to place here in equation 4. So from 4, so you know already the Q, so you place 2,400. The area that you will have here will be the lateral surface area, because that's where your heat transfer will, that's the area in which heat is going to pass through. So A is equal to HL. We solved already HL. And that's 2512. 2512 watt per meter squared Kelvin. And by the way, this one is in watts. And we have the change in the temperature again. So in here, your change in temperature will be the wall temperature minus the bulk temperature of the fluid. So remember, you remember the formula Q is equal to HA temperature of the wall minus the bulk temperature of the fluid. Our general convective heat transfer rate equation. So in this case, the delta T that you have here is not similar to the delta T that you have in here in mCp delta T. Okay, it's different than the delta T that we have for convective heat transfer. Now, we already have the H here, and that's the 2512. The A we placed here, and that's the A that you see here. So we have this one, the difference between the wall and the bulk temperature. Now, if we go back to the problem, on the given, it says that the wall temperature is 30 K above the bulk temperature. So you need not really know what this actual bulk temperature is, whether you take the average of the inlet and the outlet temperature, or whether it's a different value. You need not know that because the phrase itself says that your TW is 30 K above the bulk temperature, which signifies that this 30 Kelvin is already the difference between the wall temperature and the bulk temperature of the fluid, because the wall temperature is 30 kelvins higher than the bulk temperature. So the difference of the two is 30. So the TW minus TB here, actually this is bulk temperature, will be the 30 Kelvin. So you get to cancel the Kelvin unit here, you get to cancel the watt units, and you will have the area in square meter. So the remaining unit is square meter. In this case, your area is 3.185 times 10 raised to negative 2 square meter. Now, I said a while ago that this area is not cross-sectional area, but lateral area. So this must be the pi dl. And this is the 3.185 times 10 raised to negative 2, which you need to equate to pi times the diameter, which is 0.05, meters, and then you have the, oh, sorry. I continue it here? Still on the next slide. So you have okay, sorry about the class. I was disconnected. Okay, we'll share again. I was disconnected. Where was that? Okay, so your diameter here is 0.05 meters, and your length of the tube, which is the one we're looking for. So we'll get a length of 0.203 meters. The value of the area that we got here equated to pi dl, lateral surface area, will give you a length of 0.203 meters. Okay, so we just substituted the diameter to the pi dl formula. So the only unknown is the L, and you'll have it equated with the area here. We have computed based on QA equal to H delta T, which is the difference in the wall temperature and the bulk temperature of the fluid. So this is the thing we're after. Okay, wait, class. Okay. What part can you see now, class? Can you see the 2512? I think Jamboard was not able to record because my internet is very unstable. So you can see can you see already the Jamboard? Okay, just give us a thumbs up sign so I will know, have a way of knowing. Okay, thank you. So I think, sige, thank you, Carlos. So you'll have an A here. The area that you're going to get here will be equated to pi dl. So I will redo what I have written a while ago. So this is the value of the area that you're getting here. And you'll equate it to pi dl. That's pi times point. For the diameter, we have 0.05 and we have the length. So for the length, you'll be getting 0.203 meters. Okay. So that's the length of the pipe that the problem is asking for us to determine. So in this problem, you determine first the Pecklet number. And you need the different physical properties of the liquid metal. So you can choose the formula appropriate for the Nusselt number. So we determine that. And then we determine the HL for us to be able to determine the lateral area. So your Q can be computed based on MCP delta T, and that's 2,400. And you need to substitute the Q in here in equation 4 to get the area, which will be equated to pi dl. Okay, any questions so far? Any question? None? Sige. So we'll continue then. I'll go back to the document. Wait, class. Okay, so that's the sample problem we just tackled. Now we go to the loop mean temperature difference. Now we use the loop mean temperature difference if we have a case of fluids that are transferring heat one from the other. Now, the manner of flow of these fluids can either be co-current or counter-current and. So I'd like to emphasize this one and I'd like to annotate here. This concept is used in double pipe heat exchanger. One pass double pipe heat exchanger. So you know that you'll be using the concept of the loop mean temperature difference. Number one, if you're given the temperatures of the two fluids that are not necessarily in contact but will transfer heat one from the other, and the equipment that is being used or that will facilitate this transfer is a one pass double pipe heat exchanger. Double pipe heat exchanger in which the fluid is passing in the annular space in between. I guess I have mentioned this annular fluid or the concept of the annulus. If you have these two pipes, let's say this is your pipe 1 and inside is pipe 2, the annular, this is your pipe 2 for example, the annular space is this. Okay. So the fluid, one fluid is passing through the annular space in between the two pipes. The other one is in here. The other one is in here. So there is transfer of heat between these two fluids that are in two concentric pipes, or we call them double pipe heat exchanger. One fluid on the annular space and one on the inside part of the pipe. And we use the concept of the loop mean temperature difference in determining the amount of heat that is being transferred. Okay, now it is important, however, that the problem with the case of the use of the concept of the lube mean temperature difference should give you all four temperatures of the fluids that are being mentioned. What do I mean? The inlet and outlet temperatures of the two fluids. So it could be also that one temperature is unknown, but you can equate the two Qs of the two fluids and you get to know the other one. But as much as possible, the problem will give you all four temperatures. So T1, T2, and T1 prime and T2 prime. So in here on A, I'll just clear my markings. Here on A, you have counter current flow. So your fluid 1 and fluid 2 are facing each other. So counter current flow. So one is in this direction. I'll just enlarge the arrow. The other one is in this direction. So letter A is counter current flow. So you have the inlet temperature of the fluid here. Okay, which one? The inlet temperature of this fluid here, T sub 1 prime. And you have here the outlet temperature of this fluid, which is T sub 2 prime. So the direction of flow is like this. So its temperature is going down, telling you that this fluid transfers energy from itself to the other fluid. The other fluid enters as a much lower temperature of T sub 2. So this is its T sub 2 and it leaves at T sub 1. So this one is your delta T sub 1 and this one is your delta T sub 2. This delta T sub 1 and this delta T sub 2 are the delta T's that should be substituted here on the formula for the lube mean temperature difference. The only difference with counter current flow and parallel flow is very obvious. So in parallel flow, they enter at the same part of the pipe, let's say. So all entering at the same direction. So the arrows are pointed at the same direction. So one fluid at a lower temperature, another fluid at a higher temperatures. We expect this one to decrease in temperature just like this, and this one to increase in temperature like this. So your delta T1 in the two scenarios and delta T2 will be opposite this time. So if this is delta T1 here in counter current flow, this is now your delta T2 in parallel or co-current flow. So suli na siya sa aton language. So your delta T2 here in counter current flow is delta T1 in parallel or co-current flow. Now, if you're asking where does this delta T lube mean going to be used? It's going to be used in the formula for the Q. So instead of just using a pure delta T formula, so you'll be using the delta T lube mean. So it's it's Q being now your delta T lube mean, not just the delta T only. Okay, so for you to understand how we're going to use the delta T lube mean, here is a formula, excuse me class, concerning a heavy hydrocarbon oil. So it's not anymore delta T, which is the difference in the wall temperature and the bulk temperature of the fluid, or a delta T, which is simply outlet and inlet temperature if we're simply using the MCP delta T. But this time, your delta T is delta T lube mean. Okay, so we have this very simple problem to illustrate the use of the formula that I shared to you a while ago. So a heavy hydrocarbon oil, which has a CP of 2.3 kilojoule per kilogram Kelvin, is being cooled in a heat exchanger from 371.9 Kelvin to 349 Kelvin and flows inside the tube at a rate of 3,630 kilograms per hour. So your heavy hydrocarbon oil is inside the smaller tube. A flow of 1,450 kilogram of water per hour enters at 288.6 Kelvin for cooling. So you have your cooling medium on the annular space in between the two pipes. for your heat exchanger in this case. So it's your cooling water and flows out outside the tube. So you are to calculate the water outlet temperature and heat transfer area if the overall heat transfer coefficient that is to be used is 340 watt per square meter per Kelvin and the streams are countercurrent. Now, letter B, you are to redo everything this time if the flow is co-current or that's parallel flow. So you may take a picture of the problem again. That way you will have a reference when I discuss the solution. Okay? Okay, I'll go now to Jamboard. So please refer to the picture that you have taken on the problem. So you're given a heavy hydrocarbon oil. So we'll just have it as oil. My smaller pipe is not as long as the bigger pipes. You will see that there's a pipe inside. You may misunderstand it, so I'll just lengthen it para ara siya. So that's your inner tube. So this is where your oil is. On the inside tube. Now you're given its CP. So you can refer to what you have there. It's 2.30 kilojoule per kilogram Kelvin. So initially for this oil, so since this oil is to be cooled down, so we'll just have this as our T sub 1 prime. This is countercurrent flow. Let me just show to you again the document so you will understand. So this is countercurrent flow A. So this is the A class. Please refer to this. And your oil is expected to decrease in temperature. So I'm labeling its inlet temperature as T sub 1 prime. It's going to live at T sub 2 prime. The cooling water at an initial lower temperature will be, of course, increasing its temperature from T sub 2 to T sub 1. Okay, we'll follow the annotation here. And this will be your delta T1 and this will be your delta T2. So if you intend to recall again this one, you may take a picture before we go back to the Jamboard where we're going to place in our solution. So you will not be confused as to the representation. So your oil will have T sub 1 prime and T sub 2 primes for its inlet and outlet temperature based on this representation of countercurrent flow for a double pipe heat exchanger. Okay, so I think you have taken already the picture. We'll go back to our Jamboard. So that's your T sub 1 prime. So it's to be cooled down from 371.9 Kelvin. So this must be your T sub 2 prime. So 349.7 Kelvin. Okay? So the rate in which this oil flows, so I'll place here mass flow rate of the oil. It's 3,630 kilogram per hour. Now, as for water, so I'll just place in water here. This blue. So this is for your H2O. So it's counter current. And its mass flow rate is 1,450 kilogram per hour as well. Now, the inlet temperature of water, if you recall a representation, so the inlet temperature of water is T sub 2. Since it's the fluid that will have its temperature increased. So T sub 2 is 288. 288.6 Kelvin. Now, it's going to live. I'm just going to place here the arrow where you will have your T sub 1 for your water, your cooling water. Okay? So, you are required, letter A, the outlet temperature of water. So, that's T sub 1. And you are required for the heat transfer area. So we'll have this heat transfer area as A sub I if you're given the condition that the overall heat transfer coefficient based on the inside diameter of the pipe is, 340 watt per square meter per Kelvin. The flow here is counter current. And letter B, the only difference between these two is the formula that you're going to use for delta T log min. So letter B is on the scenario wherein it would be parallel flow. Any question, class, as to our given, the required, before we go to the solution? Any question? So no question. Okay, so I think there's no question. So we go to the solution. Before we can even start using the delta T log min in this case, because of course you will be thinking this is a double pipe heat exchanger, so we'll be using delta T log min. You have to make sure that there is a way for you to complete all 4 temperatures. Now, if there is no way, class, for you to complete all 4 temperatures, don't worry, because we'll be discussing on a separate topic on heat exchangers what would be the other way for you to solve for the heat transfer or the amount of heat that was transferred. It's not only the delta T log min that we can use in this case, but we have also other ways of determining that. We can use effectiveness, the heat exchanger effectiveness, but that's under a different topic. So we'll just discuss the topic that we have now. Okay, so question, are all 4 temperatures for the delta T log min complete? Of course, your answer will be no, because in the first place, the first question is you're asked for the outlet temperature of your cooling water. So since it's not complete, the next question is there a way for you to complete it? Using concepts of heat transfer, would you be able to determine the T sub 1 in this case, as we have labeled it or represented it? Of course, the answer is yes, because in this case, whatever heat is rejected by your oil, in this case, in the inside tube, that would be the same heat that your cooling water will receive. So the increase in temperature in cooling water will be due to the amount of energy that was released by the oil flowing inside the pipe. So you will be using a very simple case of MCP delta T of oil. So since it will be the one that's going to release energy, will be MCP delta T of the cooling water. Only that this time you have to affix a negative sign on the two expressions because one will be rejecting heat. So we expect that the amount that we will quantify is negative. So we cannot have a negative answer in this case, so because we are just wanting the magnitude of the amount of heat that is transferred. What I'm trying to say is we'll try to place here Q of oil is equal to Q of water. Okay, Q of oil is equal to Q of water. However, oil is going to reject heat. So this Q will be negative. So we cannot equate it directly to Q of water because this one is negative. So in terms of magnitude, for them to be equal, you just place a negative sign in here. Failure of yourself or failing to place a negative sign here before the Q of the oil will give you a very wrong answer. Because in this case, you are equating the magnitudes only. So it has to be all positive. So I'll place here negative of the oil. So you will have MCP of the oil, delta T of the oil. I'll just simply place O na lang. O is equal to MCP delta T of water and delta T of water. Okay? Now, I'll place the negative sign in here. Now, what's the mass flow rate of the oil? So you have here 3,630 kilogram per hour. So 3,630 kilogram per hour. Now, the CP is 2.30. 2.30 kilojoule per kilogram Kelvin. Now, the delta T of the oil will be, of course, the change in the temperature of the oil as it enters and leaves the inner tube. So we have outlet temperature minus inlet temperature. So we'll have 349.7 minus 371.9 Kelvin. So we cancel the Kelvin units and the kilogram unit. Now, if you notice, since the difference here is negative, your answer will be negative. So that's the purpose that you're placing a negative sign there to make it positive. Now, you place here the mass flow rate of water. Oh, sorry. So mass flow rate of water is 1,450. Now, what's the CP of water that you're going to use here? I'll just place it here below because we don't have enough space there. What's the CP of water that you'd like to use? So it's common anyhow. You can use the 4.187. So you use 4.187 kilojoule per kilogram Kelvin. Okay, that's for water. So we cancel the kilogram units now. And then for the temperature of the water, we're after its outlet temperature, which we do not know. And you have the 288.6 for its inlet temperature. So I'll place here T1 minus 288.6. And this is in Kelvin. So there's no need for you to convert the per hour here because anyway, they will just simply cancel each other. So kilojoules unit will just cancel each other and the R unit will just cancel each other. This T, of course, should have the same unit as the 288.6 and also same thing in here, which is in Kelvin. So you'll be getting now the outlet temperature of water. So this is for letter E. So if you're going to solve for it, your answer will be 319.1 Kelvin. Any questions so far with letter A? So no question with letter A. So in letter A, we're also tasked to determine the U sub I. Is it U sub I? No, it's A sub I given the U sub I. So this tells you that you will be needing this time already the delta T lub mean. Okay? Your delta T lub mean. So we'll have here Q. So you will have, take note as U sub I, A sub I, delta T lub mean. Okay? So a while ago, your delta T here is the wall temperature and the outlet temperature or the bulk temperature of the fluid. The delta T, if it's HA delta T. Now, in the case of heat exchanger, a double pipe heat exchanger, you'll be using this formula, UA delta T lub mean. If you're given the inlet water temperature, if you're given the inside overall heat transfer coefficient, then you make this as U sub I, A sub I. If what is given is the outside overall heat transfer coefficient, you change this to U sub O, A sub O. The delta T lub mean stays the same, as long as we're talking about the same orientation of the flow of the two fluids. So if it's countercurrent, then you use the countercurrent. So in this case, since this will be our working equation, you will have that as equation 1. I didn't have any equation yet here, so that would be your equation 1. And we'll have the delta T lub mean. So the delta T lub mean is delta T2 minus delta T1 divided by ln of delta T2 over delta T1. Okay? Now, there's a question. Can we interchange these two, Miss Ali? The answer is yes. If you make this delta T1 and delta T2, make this also delta T1 and delta T2. Okay, whatever is the order you're subtracting here, that's the order also in which you're going to divide them in the ln expression in the denominator. Now, we'll substitute. So if you recall, I'll go back to the document. Our delta T1 actually, class, is these temperatures here. Your delta T2 are these temperatures here, if it's countercurrent. Okay, I'd like to go back to the document so you will see it for yourself. Okay, so this is delta T1 and this is delta T2. It changes when it's parallel flow. This is already delta T2 and this is already delta T1. And the orientation here also changes. We have now delta T2 prime here, delta T1 prime here, delta T2 and delta T1. Okay, so we'll just go to the parallel flow later. But this one, this is your delta T1 and this is your delta T2. I'll go back to the Jamboard now. Excuse me. Okay, so our delta T2 will be this side. 288, that would be 288.6 minus 349.7. And then your delta T1, you have the one that we solved and this one, 371.9. 319.1. 371.9. Let me check if I got. 371.9. Okay. And we'll have the ln of these two differences as well. So it would be good if you already get the difference of the two, so you need not write a long expression there. So it's negative 61.1 there. And you have 52.8 negative as well. So you will have a delta T log mean here of 56.9 Kelvin. So you can check. So 61.1 divided by 52.8, you take the ln of that. And then you multiply it with negative 61.1 plus 52.8. Wait, class. Two eight eight 61.1 minus 52.8 over 61.1 over 52.8. Delta T2 okay, delta T2 minus delta T1. Two 288.6. Your delta T2 is T2 prime. Okay. When you subtract class here in the delta T's, okay, you need to get the absolute difference of this. So always subtract the lower number. Always subtract the lower number from the higher number. So in this case, we'll have this as negative and this one as positive. We'll have this as negative and this one as positive. So we need the absolute difference, by the way, of the two temperature differences. So we'll take this out and this one. Okay, higher number minus the lower number. Okay, higher number minus the lower number in the two delta T's. You'll be getting this value of 56.9. Let me check. Okay, so you'll be getting 56.85 or that would be 56.9. So your delta T's class, whether it's countercurrent or co-current, always is absolute, the absolute difference of the two. I did not mind the manner of my subtraction a while ago because I know that both will be negative. But in the case here in the numerator, it will have an effect on the negative side in between. So it really matters the order in which you're subtracting. So lower number subtracted from the higher number to get the positive delta T log mean. So in this case, that is 56.9 Kelvin. So once you have that, you can substitute it here in your UA, all based on the inside parameters of your pipe or inside fluid, and then multiply it with the delta T lub mean. Now, as for the Q, it could be any of the Qs in here. So the Q that is rejected by the oil, by the carbon, hydrocarbon oil, will be the same Q that will be absorbed by the water. So any of the two Qs. So you may choose from any of the two. So to get your AI, I place here Q of the oil, negative Q of the oil or Q of the water will be equated to UI AI delta T lub mean. Okay, any. So we won't have any problem. We'll have that of water. So water is 1450. And then you have 4.187 kilojoule per kilogram Kelvin. And for its temperature, you have 319.1. .6, and we'll have the Kelvin here. So we cancel the Kelvin units and the kilogram units. We'll have it equated to UI. The UI that is given, the overall heat transfer coefficient based on the inside parameters, 340. I'll just place it below. So I'll just erase this one. This is Q of water. UI is 340. What's that 340? Watt per square meter per Kelvin. And then you have the AI, the one that is being sought for. And then your delta T lub mean, which is 56.9 Kelvin. So you cancel the Kelvin here. The meter square unit should remain. Now here it is, class. See here in this side, you have the watt, which is in joule per second. While in this side, you have the kilojoule per hour. So there's a need for you to convert the kilojoule here to joule and the R to seconds. That way it will agree with the watt unit in here. So what we'll do, we'll erase this one here and we'll first have the conversion. So you'll have here 1 kilojoule to 1000 joules. And then we'll have, since hour is in here, 1 hour to 3,600 seconds. Okay, and I'll just place the equal sign here. So this time your hours now is converted to seconds and your kilojoule is converted to joule. So joule per second is your watt unit. So now they can be canceled with the remaining unit in our expression to be that of square meter. So that would be your A sub I. Okay. Please compute for A sub I. Your A sub I should be 2.66 square meter. Let me see. 1450. You multiply with 4.187 and you multiply it with the difference of 319 and 288.6. You multiply it by 1,000, divide it by 3,600, you divide it by 340, and you divide it by 56.9. So it's 2.66 square meter for the inside area. Your A sub I. You can also use your for oil if you want, but don't forget the negative sign. So that's for the A requirement. Okay. For the B requirement, you have parallel flow. So for parallel flow, if you're going to draw the box, this is for your oil. Oil is going to decrease its temperature. And this is for your water. Water will increase its temperature. Okay? That's parallel. So you still have your T. So you have still your labeling of the T's. Now this side will be delta T2. We'll just go back to the document in a while. So in the co-current, this is delta T1. Now this time it's delta T2. And this will be your delta T1. Now this will be T2 prime. This is T1 prime. This is T2 and this is T1. So it would, most of the mistake of my students class is in here, the confusion of the labeling of the temperatures. So I too at times mix up even in the manner of subtracting, because if you just forgot the notation, even if it's just a manner of subtracting and dividing, you will get everything wrong. So please take note of the notation. I'll go back to the document and check whether I have it labeled correctly here, just in a while. Okay, so we'll have this as your water. Okay, so take note. Delta T2, delta T1. Delta T1 here. And all twos are in here. T prime for the liquid that is decreasing in temperature. Of course, the other one will be increasing in temperature, so it doesn't have the prime. So this is our notation for parallel flow. Okay, I'll go to the document and check whether our representation is correct. So here it is. Okay, delta T2 here, delta T1 here. So T2 both on same side, just like in here, and T1 on same side. The primes is for the fluid that decreases in temperature. Okay, so that's the same actually with co-current, only that we have the delta T1 here. That is why you have the ones here and you have the twos here. I'm referring to the subscript. I'll go back to the job board. So we'll have a different delta T log mean in this case. Formula is still the same. It's delta T2 minus delta T1. And you'll have here ln of delta T2 over delta T1. The same requirement for both. So you will have delta T2 will be this and this. So your oil inlet temperature is 371.9. We subtract from it the inlet temperature of water. 288.6 if I'm not mistaken. So 288.6. Then subtract delta T1 is the delta T1 of oil prime. And the delta T, sorry, outlet temperature of oil is 349.7. Outlet temperature minus outlet temperature of water, the one we saw, 319.1. And you will have ln of the difference of these two again. So 371.9 minus 288.6, that is actually 83.3. And you have 349.7 minus 319.1. That's your 30.6. So you have a delta T lugmin here. Take the ln of that. And we multiply to 83.3 minus 30.6. So you will have 52 in this case. 52.78 Kelvin. And that is for parallel flow. You kindly check if that's correct. For parallel flow, you have 52.78. Now, of course, you're going to solve again your Q based on that. UA delta T lugmin. You can have any of the Q again here, but since we used a while ago water, so we did not get the value here. We'll get it. 1,450 multiplied to 4.187 multiplied to the difference of 319.1 and 288.6. And we have the conversion units. 51,436. So this is 51,436.13 watts. Please check my values. Where is it? For water. And you're going to equate it still with 340 and to get the AI. So we're going to equate it with 340. Anyway, it's already in watt. Then you have AI and the delta T lugmin, which is 52.78. So you will have an AI of, in this case, divided by 340 and 52.78. So you have an AI of 2.87 square meter. This is for B. That's your AI for B. Now, remember that you are asked for T1. For letter A, T1 and AI. So I have a question then, would there be any changes with the T1 here? If flow is parallel, or would this be the same? You may put the answer in the chat box or you may answer it. Since for letters A and B, we have the same unknowns. That would be the outlet temperature of the cooling water and the A sub I. So we have solved a different A sub I for parallel flow, and that's 2.87. For counter current, it's 2.66 square meter. Now, where will our T sub 1, that's the outlet temperature of your cooling water, be affected by the flow? Will it still
No,
be
miss.
okay, no, correct. It will not be affected because the formula in determining the outlet temperature of water is just based on this fundamental concept of heat transfer. One material loses heat, another one gains heat. So it's not dependent on the lube mean temperature difference. So the same T sub 1 or the same outlet temperature of water. We have noticed that there's a change in the area, the inside area between co-current and parallel flow. Now, anybody here who knows why John Puplis would have a very simple problem here, solve both ways? What do you think is the significance of getting a value for A sub I in countercurrent fashion and A sub I in parallel fashion or direction of flows? What is the purpose behind while this particular required information will be required by our reference material? Or what's your possible learning here? AI for parallel flow is higher than AI or A sub I for countercurrent flow. So as per design, countercurrent flow is more effective than parallel flow because if you look at it, your driving force for heat transfer, which is your delta T, is higher here. Your delta T for letter A is 56.9. That's for letter A. For letter B, your delta T is only 52.78. So if the driving force is lesser, the amount of heat that is transferred is also lesser. So that is why, as per design class, even in the industry, it's always counter-current flow that is preferred. Unless otherwise, there is some higher reason why it should be parallel flow. But in terms of efficiency, in terms of capitalizing more on the driving force, your counter-current flow is more efficient than parallel flow. So amo ng purpose why you have this sample problem, which at first, of course, you may say is really procedural. Ang salaan mo lang di ang pag-represent sa mga delta T's. Magbalingin ulo mo din na to gani nalipat na ko. So actually, if it's not just that, so the learning should be this. Okay? And of course, don't forget that you use the delta T lube mean when you have a complete set of 4 temperatures for the 2 fluids that are being mentioned. And second, if it's not complete, there's a way of completing it. And third, of course, very important as well, is that it concerns already a heat exchanger, a double pipe heat exchanger in this case. Now, you will encounter again this topic when we go to the topic of heat exchangers after this particular topic. Okay? Now, any question with this sample problem on the delta T lube mean? Okay, no question? Okay, I'll go back to the document. We're not able to have a break. It's okay as long as we finish this one for this afternoon. Okay, so this is for the delta T lube mean. And that's the sample problem. And I think we're ending this module now. So exactly 10 minutes before the end of our 2-hour schedule. Okay, I'll stop sharing for now.